Class is being recorded. All right. Well, let's see. Does anybody have any questions from homework that we want to address right now? Doing okay? All right. I've had quite a few questions on My Open Math. That is a really good way to ask me questions, but make sure that you're asking them. Make sure that you're not just struggling with problems and not getting help, because then you're not learning anything, you're not progressing, and you'll fall behind. So try not to fall behind. Come and talk to me, send me an email through My Open Math, through the homework is the best, and whatever else you need to do to get the help that you desire and need. So last time we ended up with, let's see, we finished chapter 18. We started, did we start chapter 19? Not really, okay. Okay, so chapter 19, which is entitled Electric Potential and Electric Energy. It's very tempting to think that electric potential and potential energy are the same thing. They are not, but they are related and very closely related. But it's important to realize that they are not exactly the same thing. But the relationship between electric potential and electric energy is actually a very similar, in fact, the same relationship between electric field and electric force. Okay? So you remember that electric field is like a representation of all the forces that could happen if a charge was placed in that position, because of some other charge that's creating those fields, quote unquote, or those potential forces, you could think of them as. Electric potential is very much that, where you have the potential for a charge to have some energy because it's put near another charge or near a charge distribution. But you don't actually have anything in there right now. The potential is just there for it to have energy if you did put it there. Does that make sense? So it seems a little bit strange that we would do this, but this is really not much different from potential energy, except that there is not something actually there to have the potential energy, right? It's just the potential of that energy to be there, the potential of that potential, if we put a charge in there. So it's that's what we're talking about when we talk about things that have a certain voltage. You know, if something has a certain voltage, that is the potential, that is the electric potential. And we often call it the electric potential or the potential difference or just the voltage. Can you think why we would call it the potential difference? Why would we call it something a potential difference? Do you remember something from gravitational potential that would kind of trigger this idea of potential difference? What was so strange about gravitational potential compared to things like kinetic energy? Gravitational potential energy and kinetic energy were both kinds of energy, but gravitational potential was unique in one particular way. For example, kinetic energy could only be positive, 1/2 mv squared, right? M is always positive, v squared is always positive, 1/2 is always positive. But potential could be both positive and negative. Why? It was mgh, and g was a constant number all the time, so you either chose it to be negative or you chose it to be positive, but that didn't change what potential energy was. What did change it? Height. Height could be negative, right? Why can height be negative? Yeah, so we choose a starting point. We choose the 0 point, right? We say we want ground level to be 0 potential energy, or we want the top of the cliff to be 0 potential energy, or we want something like 7.5 fathoms to be potential energy, 0 potential energy. We choose our 0 point. Anything below that would be negative potential energy. Anything above that would be positive potential energy. And so it is relative to the point at which we choose our 0 point, right? Potential in electrical potential is the same way. We choose a 0 point, and then we calculate everything from there. So it's often better to just instead of talking about the absolute potential compared to some particular point, which we're calling 0, in electrical stuff we usually just say the potential difference. What is the potential difference between this point and this point? Because that will always be the same. It doesn't depend on where your 0 is. You're just saying one of them is at a particular potential, the other one's at another particular potential. If we choose a 0 point for both of them and then calculate the difference, that value will always be the same. It's like calculating the height difference between 2 points, right? The height difference between 2 points is always the same, but how high they are depends on where your 0 height point is, right? So two things can be 10 feet apart, but one of them could be 1,010 feet, the other one could be 1,000 feet, or one of them could be 30 feet, one could be 40 feet, right? Or one could be negative 10 feet, one could be 0 feet, whatever.
What's the difference between what we were doing where we place a point charge somewhere, we calculate it based on all this, compared to this potential where we're seemingly hypothetically placing it there?
So when we calculated all the fields, we were also hypothetically placing the field charge there.
So is there any real difference?
There is a difference because the field was a measure of the possible force that could happen. This will be a measurement of the possible energy the charge would have. Does that make sense?
Yes.
So that is the difference. When we talked about calculating field is a measure of the possible force that a point charge would feel at that point. And potential is the possible amount of electrical energy that a point charge could feel if placed at that point. So, but you're right, they are very similar with only that small distinction. That small distinction being quite an important distinction, but anyway. So here they show this this person doing this CPR with it's an automated external defibrillator unit. They're calling it. So essentially, you can press on this, and it will actually also administer shocks. So you can use it for CPR, and you can use it for also for this device. You can see here there's this electrode here, and there's another one under her hand over here. You can't really see. But these electrodes create a potential difference, an energy difference between 2 points in the body, where the heart is in between those 2 points, right? And the heart nerves, the nerves that activate the heart, are running right up here along the left side of the body, kind of the center of the body and left side of the body. So if you place these electrodes here and here, and you put a potential, you create a potential between those two things, then charges that are in between those two things are going to feel some energy, right? And that's the whole idea. The whole idea with a defibrillator is to energize the neurons between the electrodes so that they feel a charge, and then they excite the muscles. They make the heart start. They start the heart, right?
So you're more or less just completing a circuit with the heart.
You're completing a circuit with all the charges in the body between these two electrodes. That's correct. You're creating a circuit where one of the wires or one of the resistors in the circuit is the body, right?
So that's interesting. Whenever I never really thought it's actually getting everything, but it also gets the heart, which is what
That's right. So if you've ever seen somebody in a movie or something be defibrillated, you notice that their whole body jumps. That's because their whole body flexes, their muscles in their body flex. And it's not exactly like they show in the movies. Like in the movies, they show it just kind of like a bounce. And that's not exactly what it's more like a contraction. The body will contract, and some of those muscles will cause the body to rise. Some will cause the chest to flex. Some will cause other things to happen, but your body will convulse because of the muscles will activate, including the heart muscle. So, and if you can do it at just the right potential, if you give it just the right amount of potential energy, essentially, that energy that goes into the muscles is just the right amount of kinetic energy to actually start the heart. If you don't give it the right amount of energy, it won't be enough, or it will be too much. So, you know, they actually know these things. They've done a lot of a lot of the science and the research behind it. So defibrillators are designed to give just the right amount. And so, so this is the beginning of the study of voltage. Potential, electric potential is measured in voltage. The volt is the SI unit, or the standard unit in physics for electric potential, and it is named after Alejandro Volta, who was a Spanish physicist a few hundred years ago. He invented the battery, things like this. But anyway, let's talk about what actually creates this potential difference. So here we have a plate of metal and another plate of metal. This plate over here is a solid plate, and it's charged up with positive charges. Somebody has taken a bunch of electrons off this plate. Over here, we have a plate that has been charged up with a bunch of negative charges, so somebody's put a bunch of electrons on this plate. And in between, we have these field lines going from plate to plate. Notice that near the outside edges of the plate, those field lines are not straight across because there's something bending them, these corners and so on, so forth, are bending them outwards. And you have these continually bending fields out here that they don't show that get further and further apart, so the field gets weaker and weaker and weaker the further out you go away from the plates. But in between the plates, right in this region, you get a fairly uniform field. In other words, the field lines are evenly spaced apart, right? So that means that the field strength is the same all through here. They're not showing that they're evenly spaced, but they're fairly closely evenly spaced. They're also parallel lines, so that we know that this field is going from left to right, so that if we put a positive charge in between these plates, it will also go from left to right, and they leave a little hole there so it can shoot out. This is actually a very simple diagram for what we call an electron gun. Electron guns are electrical devices designed to create a stream of electrons coming out at high potential, or high energy electrons. So they get repelled, or sorry, it's called an electron gun if it's backwards. They put the hole on this side and put electron in, sorry. But this one would be a positron gun or a proton gun or whatever. But it's essentially a charge gun, an electrostatic particle gun. And they're used in experiments all the time in physics and engineering to create a stream of charged particles coming out. This is analogous, as they say in the caption here, to a ball rolling down a hill, where this positive side for a positive charge is the top of the hill, and this negative side for a positive charge would be the bottom of the hill, right? Where in everything in between, the field in between, is where it's feeling that acceleration from rolling down the hill, right? And in the case of this one, the change in potential energy gravitational is equal to the change in kinetic energy. And the same up here, the change in potential energy electrical is equal to the change in kinetic energy. The difference being is that the potential that we usually are measuring here is not equal to the potential energy. It's related to it, but not equal to it, okay? So the potential between these two plates is not exactly this value here. So how do we figure it out? How do we define this thing? How do we make this work? Well, work and the change in potential energy is still the same thing. We still have work. The work done on something, on a particle, for example, in this field, is equal to the negative of the change of the potential energy that it experiences. The work is still equal to the force times the distance times the cosine theta. So if it's feeling a force in the same direction as it moves, then the cosine of theta, of course, becomes 1. It's just work equals force times distance. Well, remember that force in electrical stuff equals Q times electric field, right? So if we put Q times electric field in for force into here, then we get Q times electric field times distance in there. And we're starting to put together something here that's interesting. But we have a Q involved in this equation now, but the Q can be a different Q for each particle, right? It's kind of like the mass being a different mass for each particle, but mass isn't in this equation for gravity, right? Mass isn't here. So when you put this into an electrical field thing, you end up with a Q in here for this force, because force equals Q times E. But the Q, it depends on how much charge you put in there. So we decided in physics long ago to take the Q out of the equation so that we can put in any Q we want later. So we just remove Q since it's a variable and not a constant, and in any particular situation with any particular field or force or whatever. And we just remove it by saying we're gonna define this new thing we're gonna call the potential, and it's gonna have V for potential. I know that sounds strange, but it is gonna be that way. Also, sometimes they use U sometimes in physics for electric potential, but usually it is V or another Greek letter or something like that. But anyway, we're using V in this book, so the potential in this case, the electric potential V is going to equal the electric potential energy divided by the charge that would be feeling that energy. So we're going to divide out the charge, and that's kind of interesting because what is that potential energy? If we go all the way down here, let's see, where do they do it? I guess they do it in the next section. They do it in the next section. We'll save that for the next section. But anyway, this is going to be our definition for potential. It's going to be the electric potential energy per unit charge. Okay, so the amount of potential energy a charge would feel if it was put in at that point and calculated or measured. But because we do choose our 0 point, it's often much more convenient to just measure the difference in potential between 2 points. And we'll have some point that it will be considered 0 potential somewhere in the problem. Now this is usually in, so if we go back to our field lines, remember the field lines pictures that we looked at last week? Come on, go away. Okay. If we look at our field lines, and we see a very simple field line configuration, like just a single point field, like that's not, here's where we go. So we look at this field line configuration where we have a very, very strong field near this positive charge, and as we get further and further away, it gets weaker and weaker and weaker. And let's say that's the only charge in our little universe where we're learning about charges. If we want to talk about the place that has a 0 potential energy, where would that place be if that was our only field that we were dealing with? Where would the place that we would choose, where would the place that you would choose to be your 0 point? Remember the hill and the bottom of the hill, that kind of thing? What would have the 0 potential for a positive charge? Put a positive charge in here, it's going to run away from this other positive charge. But eventually, somewhere way far away, out at infinity, there won't be any more field, right? It'll be so weak that it'll be negligible. And so we often choose our 0 point to be at infinity. We say at an infinity distance away from this thing, we're going to say that's 0. And we're saying that's 0 for everything. And that often happens with electrostatics and electrodynamics. We often say, well, we've got all these field lines all over the place. It's kind of hard to define a 0 point, to say this place is going to be 0 and everything's going to be measured from there. So maybe we just call it infinity. Now, practically speaking, that makes no sense. But mathematically, it makes perfect sense. So mathematically, we can do that. And so we can do the math here. There are also many situations that we will come across where there is a 0 field in our field somewhere. Remember when we had the 2 charges, positive charges close together, and the field canceled out somewhere in between them? Let's see if I can find one of those. Here's one. So you have 2 positive charges. You have a positive field coming this way and a positive field coming this way, and they cancel out to 0 in the middle. So that would be a great place to choose a 0 point for potential energy, because nothing would be feeling any force there. Nothing would have any potential energy there, right? It would just kind of be a happy place, right? So we often choose 0 points for field as our 0 points for potential. It's not that where the field is 0, the potential has to be 0. That's not the case. We just choose it there because it's convenient for the mathematics. We don't always do that, but we often do it. When we get into things like circuits, we'll often choose our 0 point arbitrarily, because circuits always end up going in loops, and so it doesn't really matter. You always end up coming back to where you started. But we're not anywhere near there yet. So, but there are many situations where we might choose a 0 point other than infinity, or other than a 0 field point, as a place where the field has actually gone to 0. I mean, in you know, theoretically speaking, it doesn't matter where you choose it. There are just some places that are more convenient mathematically than others. And you will get some practice. It's not as hard as it might sound. In the end, it's usually quite easy, actually. So, what is the volt? A change in voltage, for example, or first of all, or a change in potential, is just the potential difference between 2 points. Take the voltage at one point, the voltage at another point, take the difference, change in potential, which is the change in potential energy per unit charge. But 1 volt is actually 1 joule per coulomb, because it's potential energy, which is measured in joules, over charge, which is measured in coulombs. So joules per coulomb, very simple unit there. If you want to go back and forth between potential and potential energy, between voltage and potential energy, it's easy. Voltage is equal to potential energy over charge. Potential energy equals charge times potential times electric potential, right? So it's just a very simple back and forth. Now, if we go back to this point here, back to this experiment here, where we had this this field created by this positive plate and this negative plate and this charge in between, and you wanted to know how fast this charge ends up going after it leaves this area here, all you'd really need to know is the potential that it felt while it was in here, right? Then you can use that potential, which is V, to calculate the potential energy, because potential energy equals V times Q, right? And then that potential energy would be equal to the change in kinetic energy outside, which is 1/2 mv squared. So you'd have to know the mass of your charge when you calculate the V. So the kinetics, the kinematics and the dynamics are still holding just like they did last semester. We'll still use a lot of the equations we used last semester to calculate things like acceleration, velocity, displacement, whatever. But let's do a calculation really quick. We have a 12-volt motorcycle battery. Now, how that's determined, we're still trying to figure that out. I'm not sure how to calculate the voltage of something, but if somebody just hands you a battery and says this thing has 12 volts of potential in it, then you don't have to calculate it, right? It says right on there. You can make an assumption that they're right. It's actually a fairly bad assumption in the end, but we're going to assume that it's right anyway. So we have a 12-volt motorcycle battery, and it can move 5,000 coulombs of charge. You ever seen a battery that has a battery rating? With cell phones, this is much more. People are seeing this much more. But if you look at any battery, I've got some batteries here in my drawer. This right here is just an Energizer Industrial AA battery. And if you look on it, it actually usually gives a rating. Let's see if I can find it. I don't see it on here. It might be on the box. Let's check the box. I don't see it here either. But it usually gives you a rating. It usually gives you a rating for the amount of energy it can supply in what we call amp hours. So it essentially tells you how much current it can supply to you, which is just like saying how much charge it can push out of the battery over time. In this particular case, they say it can move 5,000 coulombs of charge, and it's got 12 volts, right? And then there's another one that can move 60,000 coulombs of charge, right? So these are telling you how much charge is going through this potential difference, or how much charge is experiencing this potential difference of 12 volts. The potential energy, of course, the change in potential energy is equal to that charge times that potential difference. So we can calculate the potential energy of each battery. We can actually calculate the rating for how much energy each of these batteries has, how much energy each one of them can deliver. The one that has the 5,000 coulombs of charge at 12 volts can deliver 60,000 joules of energy. The one that can deliver 60,000 coulombs at 12 volts potential can deliver 720,000 joules of energy. Right? So potential energy, electrical, and potential electrical are related by the amount of charge that is moved. Right? The amount of charge that goes through that potential. So let's take a look at a 12 volt car battery. It's running a single 30 watt headlamp, this guy right here, right? And it's interesting here because you have this battery has a positive terminal and a negative terminal. And with positive and negative terminals, can you guess which way the electrons will move? They move away from negative, they get repelled from the negative terminal, and they get attracted to the positive terminal. Okay? Which is very interesting because current goes from positive terminal to negative terminal. So current actually goes backwards of the flow of electrons. And there's actually nothing flowing in the direction of the current. It's just like an imaginary positive charge flow that never actually moves. Right? Why is that? Well, we can thank Benjamin Franklin for that. Remember when I talked about Benjamin Franklin deciding which particle was going to be the negative one and which one was going to be the positive one? And he chose the electron to be the negative particle, and he assumed that the positive particle moved. Well, he had a 50-50 chance, and he lost. Don't ask him to buy you a lottery ticket, because he lost on a 50-50 chance. What are you going to do on a 1 in 300 million chance, right? Anyway, his choice was he just didn't know, and his choice was wrong. And it's not that it's wrong in some like moral way. It's just wrong because it made all of our math have this negative sign kicking around in all the time. And we're going to see this all through this semester, where there's a negative sign thrown in that is just because Benjamin Franklin chose the negative particle as the one that moves. Even though he thought the positive one was moving, it's actually the negative one. If he had just said the electron is going to be the positive one, then all these negative signs wouldn't be in our mathematics. But it is the case. So current is actually the flow, the imaginary flow of positive charge through a circuit, and electrons actually flow in the other direction. But there are situations where you can have a flow of positive charges. You can have a flow of helium ions, for example. Helium ions have a charge of positive of two elementary charges because there's 2 protons and no electrons. So you can have a flow of those, but they're not going to flow through a circuit. They're going to flow through a vacuum or through air or something like that. So, anyway. When lightning strikes, positive particles do move. They don't move as much as the electrons do, but they do move. Electrons move one way, positive charge move the other way, and you get a real positive current. But anyway, so let's take a look at this. We have a 12-volt car battery running a 30-watt headlight. Remember, what are watts? What is the definition of the watt? What does it measure, first of all? That's right, work per time, which we call power, right? So the 30 watts is the power of the headlight, right? And so work per time is measured in joules per second, right? And we know how to calculate electric potential energy, which is joules, and seconds is easy. So we're getting there. So if we have a 30-watt headlight, it is taking away 30 joules of energy every second from this 12-volt car battery, right? So if we have a 12-volt car battery and we've got 30 joules per second taken away from it, what's going on here? Well, first of all, let's set up our equation for potential energy and potential. Potential energy is related to potential by the charge. So if we solve that for the charge, which we don't know, and we put it into change in potential energy over change in voltage, we're close. We know that there is a change in potential, we know that there's a change in energy, or energy leaving the battery going to the headlamp, and it's going at a certain rate. It's going at 30 joules per second. So let's say that we lose 30 joules in 1 second, with a 12 volt battery. That would be a minus 30 in the change in potential energy for the battery. So you'd take 30 joules from the battery, that taking is minus, right? 12 volts is the potential of the battery. And that means if you take 30 joules in 1 second from a 12 volt battery, you're gonna remove 2.5 coulombs of charge from the battery. Removing, again, is the negative, right? So this equation has just told us how much charge is removed from the battery each second, right? Then, if we want to figure out how many electrons that is, we take that amount of charge divided by the charge of one electron, and it turns out to be 1.56 times 10 to the 19 electrons. It's a lot of electrons every second, right? Now, going back to our electron gun, this one is actually set up as an electron gun with the negative plate on this side, the positive plate on this side, and an electron inside in between here. This one's also set up a little bit more cleanly, where all the field lines in here are evenly spaced. So they've designed this deliberately so that it has a very uniform field inside here. When we say uniform field, that means that the field lines are all evenly spaced from each other and pointing in the same direction, so they're all parallel and evenly spaced. You pop an electron in here, it's going to be repelled from the negative, attracted to the positive. It's going to accelerate across this distance. Once it leaves here, it will no longer be accelerated this direction. It will actually feel a little bit of a pull back, right? But once it leaves here, the acceleration towards the right is over. And the pull from the outside is actually very weak, it turns out, compared to the pull on the inside. So it's going to leave here and it's going to escape and go flying off this direction. The speed that it gains as it gets out here is going to be determined by this equation where the potential energy was equal to the kinetic energy, right? The change in potential energy in here equals to the change in kinetic energy when it gets to out here. So if you release it from rest, its initial kinetic energy is 0. Its final kinetic energy will be whatever it is. And to calculate that difference in kinetic energy, you need to know the potential energy that it had, or that it gained, or that it lost, rather, while it was in here, right? Well, that, of course, is related by this equation once again. However, if that didn't confuse the heck out of you, notice that Ke is an energy, and so is Q times V. Charge times potential is an energy, right? So that means that charge, which is in coulombs, and potential, which is in volts, coulomb volts, essentially, is another unit for energy, right? So if you take charge and multiply it by potential, coulombs times volts, you get another energy. If it's an electron, what is the charge here? What is Q? It's 1.6 times 10 to the minus 19, negative 1.6 times 10 to the minus 19. And so, in other words, you can actually create a new one that we call right here the electron volt. Instead of saying coulomb volts, we say if an electron goes through 1 volt of potential, that amount of energy we're going to call the electron volt, the charge of an electron times 1 volt. So it's a new unit of energy, right? Remember back in the energy section we talked about joules. Joules were a very small amount of energy. It took 4,000 joules to boil 1 little cubic centimeter of water, or not to boil it, but to change its temperature by 1 degree Celsius, right? You change it by 1 degree Celsius, it takes 4,000 of these joules to do that. So the joule is a very tiny amount of energy. So we used the calorie instead. We used the calorie when we were talking about food, for example. When we're talking about food, we use calories because it's a much bigger value. It's 4,000, right? When we're talking about food calories, we talked about 1,000 of those calories because food calories are much bigger than the small calories. So we use different units to talk about different things because it makes sense. When we're talking about how long we live, we use years, not seconds, right? So we use different size units that are related to each other but very different in what they do. The electron volt is a very small amount of energy for us, for a human to experience, but for a particle the size of an electron, it's a good amount of energy. It'll get it accelerating, but it's not too much to just blast it out of somewhere. An electron volt, or in other words, 1.6 times 10 to the minus 19 coulombs times 1 volt, that's how much this electron volt unit is a really good measuring device for the energy of small particles. So physicists use them all the time. Chemists use them all the time. Electron volts are a very convenient measure of energy for small particles. So here is the electron volt, 1.6 times 10 to the minus 19 coulombs times volts. It turns out to be 1.6 times 10 to the minus 19 joules. Remember how small a joule was? Well, this is a lot smaller. But to an electron, it's a fair amount of energy. It's quite a bit of energy, in fact. So there's another kind of energy. Remember last semester we also used a different kind of energy when we were talking about house energy. The energy to your house is measured in kilowatt hours, right? That's a unit of energy. Kilowatt hours, there's a conversion from kilowatt hours to joules. And there's also the conversion for electron volts to joules. Right? Electron volts are much, much smaller than joules. Kilowatt hours are much, 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 much bigger than joules. Well, I think that electron volts are much smaller than joules, much more smaller than electron volt, than kilowatt hours are bigger than. But anyway, the point is that joules are not convenient for a lot of things, and so we use these bigger or smaller units of energy. The great thing about electron volts is that you can look at an experimental configuration. Let's say that we have an experiment where we have two things charged here, and we put an electron in between them. Well, if the potential between those two plates is 56 volts and we put an electron in there, how many electron volts of energy is the electron going to have when it exits? 56 volts, 1 electron, 56 electron volts, right? It's easy. You just take the voltage times the charge. The charge is an electron. The voltage was 56. So 56 times electron, 56 electron volts. Instead of saying coulombs, instead of saying 1.6 times 10 to the minus 19 coulombs, we're just saying electron, and that just means 1.6 times 10 to the minus 19 coulombs, right? So it's kind of a weird unit, but it's extremely useful to particle physicists and other physical chemists and other things like this. It's very easy to calculate experimentally and other things. Conservation of energy is going to work out just the same as it always has. Your initial kinetic and your initial potential is going to equal your final kinetic and your final potential. And you say, well, what about the non-conservative work? What about friction? In microscopic, even nanoscopic interactions between charges like this, friction just doesn't play much of a role. In fact, when you get really close down into it, how electrons behave within atoms, for example, there is no friction, zero. There's been no evidence of friction when you have electrons interacting with each other within an atom, or electrons interacting with the nucleus within an atom. Zero friction evidence at that point. And it makes sense, because remember, friction was actual physical things locked together because they were bumpy like your knuckles, right? Well, as far as we know, electrons have no shape. We've never observed one directly. We don't know what size they are. We've never been able to measure their size because they're one of the smallest things there is. What do you use to measure something that's super small? Something smaller, and there's nothing smaller out there. So we're kind of at a loss for understanding the true nature of electrons and other really tiny particles. But from what we do know, there's no friction involved. So let's calculate an electrical. Let's actually calculate a kinetic energy from electric potential energy. We're starting off here. We have a potential difference of 100 volts, and it's an electron. We have a free electron that's going to be accelerated through this potential difference of 100 volts. So if it says that it's accelerated from rest through this potential difference, then we already know something about its potential energy change. This potential energy change is going to be 100, the voltage times its charge. 100 volts times the charge of an electron. So we could say, right off, we could say 100 electron volts. This thing is going to have 100 electron volts of potential energy change and 100 electron volts of kinetic energy change. So there's your answer right there. Except it wants to know the speed, not the energy change, right? But we do know that it goes through 100 electron volts of energy change. So we could use that and use that 100 electron volts and convert it directly into joules if we wanted to, and then set that equal to 1/2 mv squared. They don't actually do that here. I'm kind of disappointed that they don't. They actually multiply out the 1.6 times 10 to the minus 19 times the 100 joules per coulomb, which is your 100 volts right there. And they do put a negative sign in there because it is, because you have, of course, you have a negative charge, but also because it starts out with 100 volts of potential, and when it leaves the experiment, it has 0 volts of potential. So that's the change is final minus initial, so 0 minus 100. So the change ends up being the minus 100. Divide by 9.11 times 10 to the minus 31 kilograms, which is the mass of the electron. After they solve that mv squared, the kinetic energy equals potential energy initial, and they get the speed here in the end. But it's still the same thing. The kinetic energy initial was 0. The potential energy final was 0. The potential energy initial was the 100 volts times charge times Q, and the kinetic energy final is the thing that they're calculating with mv squared over 2, 1/2 mv squared. So it's kinematics, it's dynamics, it's energy stuff, it's Coulomb, it's all this new stuff we're learning, all rolled up. We've put everything together we've learned in the past semester and this semester together. Okay, so now that we have somewhat of a handle on what potential is and what we can do with it concerning calculating potential energies, using it together with kinematics, now we need to figure out how to actually calculate it. Where does this number come from? You know, nobody's just going to hand us a box with our homework in it saying what potential everything's at. We might have to actually calculate this at some point. So we're going to start off with some fairly simple situations, and that is this parallel plates and simple situation. We've seen a few times now. So we've got our parallel plates, we've got our positive side, our negative side, the field in between, the uniform lines because they're evenly spaced and parallel. The electric field in here, that's not what I'm going to do. The voltage, the potential difference in here is going to be calculated as, where it's going to be represented as a delta V equals voltage AB, where A is the left side plate, B is the right side plate. And then we're going to talk about the work that is done on a particle that is put in here. The work that's done on a particle is going to equal it will equal the force times the distance times the cosine theta, but it's also, from our last section, equal to Q times the potential difference, or Q times the voltage from A to B. So we talked about that in the first chapter. That's the definition from the first chapter. So we have Q times voltage from A to B. So the amount of work that is done by the electric field as this particle moves from this side to this side is this right here. Okay? So we've got that much so far. Now, work is also equal to force times distance. We know that much. So if we put Q times V equals force times distance, and then we go to the electric field and we learn that electric field is equal to, they actually do this somewhere. I want to show you this derivation, but well, maybe they do, maybe they don't. I'm going to go to the next section really quick and see if they do this in the next section. I can never remember where they do it here. Yeah, here they do it. So electric field is essentially the force, the Coulomb force divided by, where you divide a charge out of it, right? You take out one of the charges and you pretend that you can put any charge in there. So if the electric field is force divided by charge, and work is equal to force times distance, right? Then you can solve the equation work equals force times distance equals electric field divided by charge times distance. You can solve that equation to get this equation right here, where electric field ends up being equal to the voltage divided by the distance in this particular situation, where you have a voltage between these two plates and a distance between these two plates. So this becomes an important equation for this uniform field situation. If you have a uniform field where you have parallel field lines, evenly spaced field lines, the electric field there can be calculated by taking the difference in potential between 2 points in the field and dividing by that distance in that field. That will tell you the electric field. And then you could also calculate, if you reverse this, you could reverse this so you're calculating the electric field. It turns out that you multiply both sides by D and you get voltage equals electric field times distance. So that starts to be interesting. And that's where we're going to go with this. We get down to this point here where we have the Q times E times D equals Q times V. And then you can solve this for the voltage between 2 points is equal to the electric field in that region times the distance if you're in a uniform electric field, or electric field equals voltage divided by distance if you're in a uniform electric field. Okay, so let's use this really quick. We've got a maximum field, a possible maximum field in dry air of 3 times 10 to the 6 volts per meter. What does that mean? In air, when you create an electric field, you start messing with the molecules in the air. The molecules in the air, if they've got some kind of polarity to them, some kind of electric field themselves, they will line up with the field. In fact, they will line up opposite the field. So it's and it can stretch the particles. If the particle, because all molecules are made of positive and negative charges. Those charges are going to go different directions in an electric field. The negative charge is going to go one direction, positive charge is going to go the opposite direction. It can rotate the particles in the field, stretch the particles, it can move the particles, it can do all kinds of things. So, so at some point, if you put a strong enough electric field in in air, in dry air, it'll actually take the electrons and rip them off of the atoms or the molecules in the field in the air. Once those electrons are ripped off, a spark will jump. It might be lightning, it might be the spark between a Van de Graaff generator and the ground, or a professor, or whatever else. But a spark will jump. You will hear and see the result of this action. Okay, there will be something that happens. That's what we call the breakdown voltage of air. So in dry air, the breakdown voltage is about 3 million volts, or the breakdown field, in fact, the maximum field strength. But that maximum field is about 3 times 10 to the 6, or 3 million volts per meter. Okay, so if you have 3 million volts between two plates and they're 1 meter apart, you'll see arcing go across there, right? However, if you have 3 million volts and they're 2 meters apart, there will be no arcing, because it's 3 million volts per meter. If they're 2 meters apart, you have to have how many volts for it to arc? 6 million volts, right? You have to have 6 million volts for that arc to happen if they're 2 meters apart. So distance matters. If you have two things that are sparking from one to the other, you're just moving apart, right? You don't get shocked by an electric fence until you're up next to it, right? And even then, you don't really get shocked until you're practically grabbing it, right? You have to be really close to an electric fence because it's not 3 million volts. It's way lower than that. However, if you have wet hands and it's humid outside, you can actually get you can get shocked by an electric fence without touching it. Because as things get more humid and as your skin gets more wet, that voltage, that necessary energy, in volts per meter, necessary field strength rather, in volts per meter goes way down. So anyway, we're given this maximum field strength so that we can calculate the distance between, calculating the potential difference between the plates. So here we have two parallel conducting plates separated by 2.5 centimeters of dry air, and we want to know what is the maximum voltage we can put on these plates before it sparks across. So we have voltage equals electric field times distance. That's one of our equations we've learned here. Electric field is going to be the 3.0 times 10 to the 6 volts per meter. The distance is going to be 0.025 meters. Turns out that you can put 75,000 volts across those plates without a marking. If there's no air in between the plates, what happens? So you think it'll go? You think that maximum voltage will go up or go down? If there's nothing in between the plates and air between them before, what's going to be? Is the nothing? If you vacuum it out, is the nothing going to be better at stopping this arc or worse at stopping this arc? Think it'll spark more easily? Think it'll be better? You think it'll spark less easily? So the air actually gets affected by the field, and then it can actually get to the point where it separates the charges, and then those charges are free to move, and they do. Yeah. And the electrons start to move, and so you start transferring charge from one thing to another. So that's what happens in air. In a vacuum, there's no charges to separate at all. And so you can build up that charge and build up that charge until the actual charge from the plate has to jump off the plate. Then it will leak across. But you have to give the electrons that are actually in the metal enough energy to jump from one plate to the other. You have to give them enough potential energy that they can turn that into enough kinetic energy to get from one plate to the other, traveling through a vacuum.
So the air is assisting in the transference.
The air does assist in the transfer. But there are other materials that do even better than a vacuum. There are some materials that will actually react to the electric field between those things and make the electric field smaller. So they'll line up in the opposite direction. We call these dielectrics, which we'll learn about in a second. So this highest voltage can change depending on the distance between the plates, but it can also change depending on what is in between the plates.
So if it was more humid instead of dry, that number would be small.
That's correct. Well, actually, what are we measuring? No. So yes. So if it's more humid, water usually has the effect. So if it's pure water, this number will actually go up. Pure water will behave in such a way to lower the electric field for a given amount of charge, so that you have to add more charge to get the same amount of field before it sparks. Dirty water with salt or sugar or something in it that has some kind of ability to ionize inside the water will have the opposite effect. So essentially, things that you can create free electrons easily in are going to create a lower potential. You're going to be able to put less charge on your plates. Things that have a tendency to react opposite the field and lower that electric field in between the plates will increase it. And there are both. Metals have a tendency to lower it, and other things that are not metals have a tendency to raise it. So pure water, being pretty much just a non-metal, made of hydrogen and oxygen, two non-metals, has a tendency to, and it's also very polar. It will have a tendency to make that potential go up, that maximum potential. Now that seems a little bit strange, but we're going to get around to showing that in better detail for you. So let's talk about the field of force inside an electron gun. We have an electron gun. We have parallel plates separated with 4 centimeters, so we know the distance is 4 centimeters. We know the voltage is 25 kiloelectron volts. We want to know the electric field strength. Well, remember, electric field is just potential divided by distance. So 25 kilovolts divided by 0.04 meters, that's 4 centimeters, 6.25 times 10 to the 5th volts per meter. Easy calculation. But for part B, they want to know What is the force this field would exert on a piece of plastic with this amount of charge that gets between the plates? So what's the force you would feel in this field? Well, force is equal to Q times energy, Q times electric field. So the charge is this charge. The field is, we've already calculated part A, it's easy. No big deal. So another way to express this is that when an electron moves through a field, following the field lines, it travels some distance along those field lines, delta S. The reason they say delta S is because it doesn't necessarily have to be in a straight line like delta X would be. It can actually be in a curved line along this field if the field is curving. So the amount of the electric field in a region is equal to the change in potential over a change in distance along the field, or a change in potential along the curvature of the field. You can think of that. So this is a more general definition of the one that we have up here, where E equals V over D. This is, this is good to talk about when you're talking about straight line distances. But in general, you do have this equation where you have this delta S. And what is that negative sign there for? Can you guess? Benjamin Franklin. Right? Up here, we didn't really even put the negative sign in it because we're just calculating the magnitude of the field. But when we start to think about direction of the field, we also have to consider that there is this negative sign. So, and this is the beginnings of some of the most important equations of all time, right here. The relationship between field and potential is a hugely important equation. It led to what Einstein did. How many sections do we have in this? 7, so we're not halfway through. Okay. So now let's actually calculate it. Let's actually calculate the potential. We've already calculated the field. Now we have a relationship between field and potential. So now we should be able to calculate the potential, right? This is the potential of a point charge, but where does it come from? Well, here is the electric field. Electric field is force over charge. Force is K times Q over R squared. So if we divide out one of the Q's, we get just K times Q over R squared for field, right? So K times Q over R squared for field. But if potential is equal to field times distance, then we would take this thing and multiply it by R to get the potential, right? Because R is the distance. Now that's a very kind of waving hands explanation of this. To do the actual math of this, we have to do it in a general. We have to do it in a general sense using some pretty nasty geometry and some pretty nasty calculus as well. But just kind of waving our hands. If we got a divided by distance squared and we multiply it by a distance, we're going to get rid of one of these r's down here. We're going to end with just r in the denominator, right, instead of r squared. And that is, in a nutshell, how we calculate potential for a point charge. So this works if you have all your charge concentrated in one point, calculate your potential there. Just like in the last chapter, remember in the last chapter we had the situation where we had charge spread over a sphere, and if it was spread over a sphere and we wanted to calculate the electric field outside that sphere, we could just we could pretend that all that charge was at the center of the sphere if we were outside the sphere. But if we were inside the sphere, it was a different thing entirely, right? So we can do the same thing here. You can calculate the potential for a spherical charge distribution as if all of that charge was concentrated at a single point. And then you can do that for outside the sphere. But if you're inside the sphere, all bets are off. You have to actually do the math. So you have very similar symmetry issues here. If you have that great symmetry outside, you can use it inside the sphere. We're going to have to learn how to do that here coming up. But here is the electric potential of a point charge or the electric potential outside of a sphere with a even charge distribution on the sphere, with a nice uniform charge distribution on the outside of the sphere. In this case, we are choosing our potential at infinity to be 0. So this is true if infinity is our 0 point. If infinity is not our 0 point, we're going to have to rethink things. But in most cases, especially in this class, our 0 point will be out at infinity, so we're good to go. So if we take a small metal sphere, right, and we want to calculate the potential produced by a small metal sphere outside. So here we have, what's the voltage 5 centimeters away from the center of a 1 centimeter, so we're outside of the sphere, right? Because we're 5 centimeters away and the sphere is 1 centimeter in diameter. And that sphere has a negative 3 nanocoulomb static charge on it. Since it's a conductor, it says right here that it's metal, so it's a conductor. And because it has spherical symmetry, it's a sphere, that charge is going to spread itself out uniformly on the sphere. There's going to be an equal distance between all the charges on the surface of the sphere. So this qualifies for using this equation that we just used. V equals kq over r, where q is the charge distribution we're interested in. So we plug in our numbers, we have our k, we have our q, the sign, and we have the distance to the point that we want to measure that potential at. Turns out to be negative 539 volts. Right? Excuse me. Let's do the same thing with the Van de Graaff generator. We want to find out how much excess charge is on the outside of a sphere for a Van de Graaff generator. Excess charge meaning charge that's not matched up with in some kind of atom. The charge that is free to move around because it's not associated with any particular atom. We have a 25 centimeter diameter metal sphere, 100 kilovolt surface, right? So the distance that we're going to calculate at is 25 centimeters because we want to know what's on the edge of the sphere. And the field, or the potential difference is 100 kilovolts that we're dealing with. V equals kq over r. What's the thing we're trying to calculate this time is the q. So q equals rv over k. And we just plug everything in. Done. It's that simple. Don't get too happy. It's not going to stay this simple for long. Now, how are we going to think about these potentials? We've already created this system for thinking about fields. How are we going to think about the potentials? So here's one way we could think about them. If we draw lines that loop around and connect to each other, not lines, but these curves, they loop around and connect each other at different potentials. So we're going to say that our zero potential is out at infinity, and let's say that we want to draw a circle where we have 1 volt. This is a positive charge, so near we're going to have positive potentials if zero is at infinity. So let's say I want to draw a circle. I want to put a point everywhere I find a 1 volt potential. Okay, so if I measure it with a voltmeter and I measure 1 volt, I'm going to find that around the point charge, or a small spherical charge, I'm going to have these spherical lines. That innermost one might be 1 volt, the next one might be 2 volts, the next one might be 5 volts, and maybe whatever. But these are what we call equipotential lines, or equipotential surfaces, because in 3 dimensions that would actually be a spherical surface, right? So these equipotential lines are places where the potential is the same. Notice that they always connect to each other, to themselves. The equipotential lines always come around and connect back to themselves. Everywhere in the universe. And they also never cross. Because wherever you have an infinite potential, you have an infinite potential to have infinite energy. There is no such thing as infinite energy, right? So these things will never cross, and that's been shown to be true. They're very easy to create. Whereas field lines, electric field is actually much easier it's much more difficult to measure. Potential is very easy to measure. It's actually, the device that you use for it is easy. We'll learn about it later on. But it's a very easy thing to measure. So, but field line requires a little more difficulty. It's a little more complex. So what are we noticing here between the field lines and the potential lines? You notice anything interesting? May seem trivial, but it's not in the end. Is there a consistent angle between field lines and potential lines here? It is 90 degrees. Right? If you have radial lines from a point and then concentric circles around a point, the radial lines will always be perpendicular to the concentric circles. Okay? And it turns out that this is true even if you have a funny shaped charge and funny shaped fields. That potential surfaces will always be perpendicular to field lines everywhere. It's always the case. This was another discovery that led to another equation that led Einstein to many of his theories. So electric field lines and equipotential lines, places where these lines that you can draw in where the potential is always the same, like 5 volts or whatever it is, and the field lines that represent the direction and the strength of the forces that can be felt are always perpendicular to each other in electrostatics and electrodynamics, in fact. They're always perpendicular to each other. Extremely important discovery. There's not a mathematical, theoretical reason for this in classical physics, in the physics that was studied. I'm not even sure there is one in modern physics. I can't even think of, well, I guess there is kind of, but they're all so intertwined that it's kind of hard to, it's like a chicken and the egg thing. But anyway, but this discovery led us to some very important stuff about electricity and magnetism. Also, because electric particles, electrically charged particles, always follow the field lines in an electric field, they're always feeling a force in the direction of field lines is a better way to say it. They don't always follow field lines if they already had some velocity that was, contrary to the field lines, but they will always feel a force in the direction of field lines. Then you can always say that in any particular place inside of a potential, a charged particle will feel a force perpendicular to the potential lines as well. Right? So that can always be said. Now, a lot of the things that we're learning in this class right now are not things that are provable. They're just things that have been observed to be the same all the time. Just very similar to gravity always pulls things towards the earth. When we didn't understand that gravity always pulls things towards each other, all kinds of things, right? These things are assumed, and as we observe more and more things, and we observe things that are contrary, then we have to change our assumptions. These are laws. These are laws of physics. And you have just learned a couple of new laws of physics that are still laws of physics that have not been contradicted yet. Things like the law of conservation of mass has been contradicted. But this is not. Conservation of charge has not been contradicted. This idea of field lines and potential lines always being perpendicular to each other has not been contradicted. Incidentally, it's a very similar thing on a map, on a topographical map of the Earth. If you have a topographical map of the Earth, they draw on these equal what do they call them? No, they call them equal altitude lines. So you have these lines on the topographical map that show you where 4,000 feet is on a mountain, right? So let's take a look at that really quick. It's quite important. So this is something we don't see very often anymore because we don't use them anymore. Topo. So these are actually called topographic lines, technically, but what they are is they're equal altitude lines, right? So each one of these lines, so they go along the mountainside and they walk along the edge of the mountain without ever going up or down. And then they draw a line that follows that path on the map, right? So you can see that if you follow this line, one of these lines all the way around, You would never be going up or down the mountain. You'd just be walking along the side of the mountain, right? You can also tell where the steep parts of the mountain, right? There's a canyon in this picture. Where's the canyon? Right here, right? How do you know that? Because all these lines are super close together and they're all moving along through here, right? You can also tell where there are peaks and valleys. And some topographical maps are colored, so it's really obvious which ones are peaks and which ones are valleys, right? Some of them are labeled, some of them are colored. There's different ways to do this. But you know, some of them are labeled with actual altitudes and so on and so forth. But and some of these lines are labeled. Like this one is a 5,000 foot line right here, right? So that's a 5,000 foot line that comes along through here, and it's a bold, and it's usually 1,000 feet to the next bold line. So this one right here would be the 6,000 foot line, and so on and so forth. You can tell where the steep parts are because the lines are really close together. You can tell where the parts that are not steep because the lines are really falling apart, right? Out here in this little valley here, there's nothing. Hardly any lines. It's just nice and flat. And that is true of field lines as well. Where the field lines are closer together, if these are equipotential lines, then the first one, if these were equipotential lines for this particular charge, this would not be correct. Because equipotential lines for this kind of charge would be closer together, would start off very close together, and then get further and further apart as you go out. Why? Because what we're looking for is we're looking for even steps between the lines. So the first line would be 1, the next 1 volt, the next one would be 2 volts, the next one would be 3 volts, the next one would be 4 volts, 1 volt steps, or 10 volt steps. The first one's 10 volts, the next one's 20 volts, or 5 volt steps. The first one's 5, the next one's 10, 15. But a true equipotential drawing for this looks different. So let's take a look at what that might look like. So for a point charge, a single point charge, a pint charge, we're going to the pub. So for a point charge, the equipotential, that's not right either. Here it is. This is what the equipotential lines actually look like for a true point charge. They're very close together at the beginning, so if the steps on this one were 1 volt steps, then that inside one, very, very closest one would be 1 volt, and then the next one would be 2 volts and 3 volts. But you can see that they get bigger, the distances get bigger in between them, because the voltage steps take a longer distance. In other words, there's a steeper climb in the middle, energy-wise, and it kind of flattens out as you go further out. If you want to translate this into forces, the forces are much stronger close in, and much weaker further out, right? Change in energy happens much more quickly when you're close into the charge over distance. But as you get further and further out, you have to go further to get that same change in energy. Right? Lots of different ways to talk about it, but it all means the same stuff. This just is not an equipotential. These are not equipotentials, right? This could not be, because they're almost exactly the same distance, right? You have the actual distance there just doesn't make sense. What you can actually say is that the closeness of these lines, if these are equally potential differences, the closeness of these lines is going to be dependent on the closeness of the field lines. The closer the field lines are together, the closer the equipotential lines will be to each other. And the further the field lines are apart, the bigger distance they're going to be between potential lines as well. So this is not a very good description of that. These ones like this are much more, well, that one's not even very good. Unfortunately, a lot of people draw these things but don't draw them very well. And then you get into situations like this where the equipotentials start to look very, very strange, right? They start to look very different. So, because you get, here's another equipotential one. Could you figure out where to draw the field lines in here? You have 3 charges. What are the fields going to look like? Let's say charge 1, you have charge 1, charge 2, and charge 3. you have negative potentials. So these field potentials look like they're in steps of 5-ish. So you got negative 5 on the two Qs and a positive 5 on the Q1, Q2. Negative 5 on Q1 and Q2 and a positive 5 on Q3. Can you tell me which one of these is the positive charge if our potential here in the middle is 0? So right here they're saying this is 0 volts and this is plus 5. So these are 1 steps. These are 1 volt steps in between. 0 volts, 1 volt, 2 volt, 3 volt, 4 volt, 5 volt. 0 volts, 1 volt, 2 volt, 3 volt, negative 5 volt. Right? That way. So which ones that are negative, which ones are positive? If you're getting more and more negative potential as you're going this way, then these are negative charges. If you're getting more and more positive potential as you're going towards this charge, this is a positive charge, right? So where are field lines going to start? Do field lines start on positive charges or negative charges? Positive charges, and then go away from positive charges. And if I draw a line, a field line from here, what's it going to do as it crosses these potential surfaces? At what angle is it going to cross them? 90 degrees. So if it goes this way, it's going to go 90, 90, 90. But once I get out here, 90 degrees is actually, I'm going to have to turn a little bit this way. And I'm going to have to turn even more this way. And then I'm going to have to turn almost going this way. And then I'm going to have to turn, and then it's going to come over here and it's going to do what? Hit that one, right? It's going to go right into that one. So you can actually draw field lines from potential lines and potential lines from field lines. It's not easy, but you can do it. It's much easier to draw field lines from potential lines than vice versa, I think, because you can measure potential lines very easily. But it can be done. Go away. I hate that dumb toolbar. Can't even do anything about it, really. Okay. So I don't love this picture, just to say the least. It's not terrible, but it's not great either. Okay, so we often use the ground as a zero potential point because it has so much free and available charge that it behaves very much like a conductor in an electric field. And we know that a conductor in an electric field has zero charge or zero field inside of it, right? In statics. And so it's a good place to call zero. So we often connect things to ground to give them this zero potential or this zero field or this place where it can draw or dump charge so that it's always kind of at a neutral, in a neutral position, you could think of it as. So that's what we call grounding, and you did that in your lab when you touched something. Your feet are touching the ground, so you're constantly exchanging charges with the ground, and then you touch the electroscope and you cause it to do whatever it needs to do to be happy, right? Either it takes charges from you or it gives charges to you, or whatever it does. That's called grounding. Now in electronics, that's quite important because in our electronics, everything that your computer does, for example, is dependent on electrons in some way. Some electrons moving here and there and all over the place. Electrons are doing something in there. If the computer has extra electrons jumping around because it's built up some charge, that's bad. That's really bad. Because those electrons will jump onto the electronics of the computer and mess up what the computer is doing. And so all computers are surrounded by a metal shield, and that metal shield is connected to ground in some way, right? In your cell phone, how do they do that? Yeah, that's a little tough, right? When you're holding your cell phone, you can be the ground. But when it's in your pocket or somewhere else, or doing something if it's disconnected from you and it's got a good insulator on it, it's got a little bit of a problem. So they've had to do some tricky things with cell phones to give them what they call a floating, they're essentially a floating electronic. But, old cell phones were messy. They did not work very well because they were still figuring these things out. Even the newest, even some of the newer versions of smartphones for example, the iPhone 5, I think, was one of the ones that had a big problem with this, where if you didn't put a case on it, it struggled to do what it needed to do, to use its antenna. It wouldn't receive calls very well. It had to have some kind of case around it because that iPhone had a back that was glass and a front that was glass, two insulators that were glass. So they would build up static charge very easily and cause disruptions within the phone. The best phones today are made of a lot of metal. Even if the outside case is plastic, as soon as you take off that outside case, inside there's a layer of metal, usually aluminum or steel or something. Some of the phones are made completely out of metal these days. You can't always tell, but they are. They're made of metal so that it grounds very easily to your hand, and any excess charge just drains off. Or if it needs some extra charge, it pulls it up, whatever. So, but this is extremely important. Even your plastic laptop, or if you have a plastic laptop, open that thing up, immediately under the plastic, it's metal. It's just metal. These computers that are made completely out of metal have just eliminated the middleman. Just why have plastic if you need metal anyway? Just make it out of metal. The hard thing is to make the metal look nice. Okay. So here they have this little thing where you can actually go and practice putting charges out here and making your fields, and you put sensors in here and sense the forces that are feeling. Put in some more charges, make the fields really crazy. And if you want to get really nuts, let's see, you want to get really nuts, you can put in the voltages, grid, some values, and where's the potential? I thought they had a potential line here too. I guess they don't. Yeah, here they want to put an equal potential. Draw it. How do you do that? Oh, here. I see. This thing is measuring potential. You can't really see it. It's too small. But this is like a voltmeter. It's measuring potential, so you can go around and find out where the equal potentials are. So if I try to look for example, 5, here's 5 volts right along here. If I go along here, try to keep it at 5, you'll notice that it kind of goes around this charge in kind of a circle. It's not a perfect circle because there's other charges involved. Some kind of like peanut-shaped circle or whatever. But anyway. So you can mess around with that and get a feel for it. And that takes us to section 19.5, which we will wait until next time to learn about. So, homework for this week. How many problems did I give you? Did I give you 1 million? Oh, not bad. 12 questions. So here's an example, another example where they're using U and V together, where U is now going to be the potential energy. So just be aware of that. In the textbook, they're using PE. In the homework, they use U. Do this in physics all the time. We're just trying to get you used to it. So U is, they're using U for potential energy, V for potential. There are even some places, and it's capital V for potential, little v for velocity. Make sure you keep those all straight. This is really the reason that physicists use almost the entire Greek alphabet in what they do. You've not seen it yet, but we use things like there's a Greek letter called Xi. And it looks like something like that. I never could really actually draw it, but I usually just did something like that, and it was like different every time. But that was my Xi, and it's it's pronounced or it's spelled in English like this, or sometimes this, or something like this. There's C. And of course we all use theta and E, and I don't know what other ones we use, but there's this one, and there's this one, and he's got so many of them, and we use almost every single one. There's very few Greek letters that physicists don't use. In fact, I don't think there are any. I think we've actually invented a few that even the Greeks don't use. But the reason is because there's so many different variables we use. We do so much mathematical modeling of the universe that we just run out of things to use. So we got to use everything we can. So anyway, I'm going to turn you loose on chapter 19 and go ahead and get started. And tomorrow we'll do a lab, and on Thursday we'll finish up this chapter. And I will post this video and make it available. And we're done.